acid bases and reactions of acid bases, and some salt work, yes, and some lab salt work we'll do later, but this is the next chapter. We're doing chemical changes, so types of, like, redox was a type of chemical reaction, acid bases were a type of chemical reaction. Now we're going to talk about things that are observed or things around a chemical reaction. There is how fast something reacts, how much energy it gives out, how far it goes, equilibria, all that stuff. There's all properties of a chemical reaction. Ouch. Yeah. Mesam, we'll figure that out next class. Abhi to I haven't sorted back to that yet, but inshallah very soon we'll figure that part out. Okay. Abhi to it is so far. I'm trying to figure out a way that I'm gonna do the YouTube thing for free, but not answer anybody on YouTube, have comments saved there, and do the Zoom as a paid interaction, because I tried making Zoom free for everybody, and there were people who just randomly sign a Zoom bomb, say shit and destroy the whole class and leave. So, and then anybody who wants to interact will get on Zoom. Anybody who wants to just watch the lectures, they'll go on YouTube. So if you are wanting a free class, wanting to study for free, you can always have access to the YouTube class. But only those who are in this class will have access to question answers with me. So I do like the question answers, and we'll have that, but I'll keep the YouTube free. But I will not be able to monitor YouTube or have people ask that question on YouTube, if that makes some sense. All right. Okay, so I don't know what this guy was saying. Okay, so let's start, huh? That's me on there. Okay. Yeah, so we got classes happening there, and all right, done. So Zilawar didn't work. It was the same as before, right? We were having that. Thank you so much. I wanted to do it free for everybody, but it was not happening. So for me, the money is just a way to get people to be serious and only have that. I'm not looking to, this year around to worry about too much about money from O levels. All right, it's not something I'm looking at actively, if that makes sense. Next year maybe, or but not this year. It's just something I'm not very actively looking at. Happens, it happens. Okay, so let's start. I'm gonna share my screen also now. Okay, we are doing energy from chemical reactions. That's the game. That's the name of the game. All right. How you guys all been? I'm so glad to see some regulars from earlier. Thank you for joining us again. I know. Master, hi. All right. Awesome. So, okay, now. Okay. Can I get some water? If you guys just give me a second, I'm just gonna get some water. All right. Okay. Dilawar, my next session for O levels, I don't know, because okay, we'll do that. Awesome. Abhi to after the exams, I'm not thinking that far ahead. All right. Not thinking that far ahead at all. So let's start. ठीक है. Sharing my screen. I will do it much more efficiently now. That's the whole point of moving here, getting more seriousness back into this class, and getting you all sorted for the exam. Yeah. Okay. Okay. All right. Yes, IGCSE. Yeah. All right. So let's start. So this is the next thing we're doing. Okay. So what we're starting off with now, we're going to look at the idea of energy changes in chemical reactions. So energy changes. Now, to understand this and to underscore what we're going to see ahead, remember one thing about, in physics, you probably have heard of it, the law of conservation of energy. And what is the law of conservation of energy? Just one second. I just realized that kids are not seeing my screen on, yeah. Okay. What was it? Yeah. There you go. Okay. So now, yeah. I've done the chapter in physics. That's great. All right. So let's look at this. You'll not get to see my face for a bit, but everybody gets to see the screen right now. Okay, that's the price we pay for studying right now of chemistry. All right. So let's continue. So the law of conservation of energy simply states that energy cannot be created or destroyed. It's only transferred. Even if it visibly doesn't seem like it, energy is always transferred, not created or destroyed. Now, and let's take the most basic everyday example of an energy change reaction, so that I can use that to explain what's happening. Now, this energy change reaction, if you live in a third world country, especially still, okay, is that when you are on your stove, now in many countries, food is cooked over natural gas, and that's part of your gas supply that comes in your kitchen. So that's the gas in your kitchen. Now, if you know that, I mean, if you have cooked anything or heated anything, you have to heat. I mean, you have to burn natural gas, and it's also known as the combustion of natural gas, and that we'll do in organic chemistry. So, but combustion of natural gas is a chemical change, and in many cases the equation for that combustion is CH4 plus 2O2 becoming CO2 and H2O. Now this is a chemical reaction. It's an oxidation reaction, and in many ways you can figure out its oxidation because you've done oxidation now, and you can follow the oxidation states of these guys. For example, if hydrogen is always +1, it'll stay +1 in both cases, but carbon here is -4, but carbon becomes +4 here, while oxygen goes from 0 to -2. In a way, you can say the carbon element in methane, which is natural gas, is oxidized by oxygen. And another name of oxidation by oxygen is also combustion. Combustion in English, and I know you did types of reactions earlier. Combustion is burning in oxygen. So this is a type of reaction, combustion of methane. Now, combustion of methane, which is a natural gas, that's literally happening every day. You warm something on your gas stove. It looks like it increases energy. You produce heat. So for the common man who is not scientifically literate, the burning of methane gas seems to, in addition to producing the product, it also produces heat. So it might seem to people that, hey, energy is being created because we are producing heat, right? That's what it seems like. Now, the thing with that is that there is heat being produced, but energy isn't being created. Energy is being transferred. All right? Now, how is energy being transferred? And now I'm going to use another common term that we might have heard of. Natural gas is a fuel. What is a fuel? A fuel is any chemical the human race uses to burn something and produce energy. Fuel means that. Fuel literally means we need energy, we get it from this chemical. It's a fuel. Burn it, get energy. A common fuel is petrol, diesel, jet fuel. These are all fuels. You burn them and you get energy. So it might seem that fuels are producing heat. So when fuels burn, so fuels seems to produce heat. But they don't create energy. What they're doing is they are converting a certain form of energy into heat. Now, if they were living things, you would say they're converting something inside of them to make heat, and that energy that is not visible to us but it exists is given a very common name. It's called potential energy. So when fuels burn, fuels are fuels because they have a potential to give energy. So when you burn them, their potential energy is being converted to heat energy. That's what's happening. Potential energy being converted to heat energy. This is during, you could say, fuels burning. Now, you might have seen the word potential energy in physics also. There are many forms of potential energy. Let me give you an example first. Potential energy can be due to multiple things. Can be due to the chemical composition of something. I'll give you an example of things that have chemical energy. The fats and the sugars you eat. Food. Food has energy. Food has energy because the food that you eat has got chemical potential energy. Because it has chemical potential energy, it's there, you eat it. You don't feel that it's hot. Uncooked and unbaked apple still has energy. Not because it's hot, but because it is innately storing energy in its chemical form, but not measurable form. Elastics also have potential energy. The elasticity rubber, if you stretch it and leave it, it flies away because it has elastic potential energy. Things drop from the top of the building, fall to the ground because they have what we call gravitational potential energy. So this is a lesson in physics also a little bit, that there are many forms of potential energy: chemical, elastic and gravitational. But we are only in chemistry concerned with chemical potential energy. Any questions so far, guys? I'm all ears to answer questions first and then go on to the next part. I'm trying to understand, basic understanding of. I should resume the recording of this class also. Sorry, guys. Hi, Ramesh, Farwa, Dilawar. How are you, Dilawar? Sorry. Arisha has 4 OKs. Can I repeat which part, Rida? I'm good. All of it? You mean the last 20 minutes of all of this? What? Good question. Good. Okay, the potential energy part. Okay, I'll repeat that part. Mason has a very good question, Mason. Now, I'll explain potential energy and also then tell you where this potential energy comes from. It comes from somewhere, obviously, right? But what potential energy means is, because you see, there are some forms of energy that is measurable. I'm just giving you layman physics terms. So you have energy. There are some forms of it that are measurable. What is some measurable energy forms that you can measure in the lab or everyday tools ke saath? Kinetic energy, because you can measure speed, right? Heat energy, why? Because you can measure temperature, right? What are the forms of energy that you know of? Do you know of any? Come on, do you know of any? Thermal is heat. Anything but thermal is heat. So thermal is also heat energy. So thermal. Now potential energy or gravitational energy is basically the ones that we can't measure easily. Yeah, you can calculate it, but you can't measure it. Are generally falling under the potential energy category. Now, what forms of potential energy do we have? If you have energy due to height, and you do this in physics, gravitational potential energy is the energy you have due to height. You have elastic potential energy. Now I'm telling you have chemical potential energy. And you have sound energy, but you can measure sound energy absolutely, because you can measure decibel levels and you can measure that. Hi guys, I got disconnected. My electricity power outage. That's what happened. Crap. Hello, sorry, my electricity disconnected. I had a power outage and everything shut off. Hi guys, hello. Yeah, I'm back. Hi guys, my electricity got disconnected. Completely power outage. So I'm back. Can you hear me? All of you? Sorry about that. I'm really sorry. This just happened. I had no control over that. I was in such a beautiful flow. You know. Why does it always happen with this particular class? Seems like this class is jinxed. Alright, so let me go back to that. You have the screen now. Let me share my screen. Yeah, I know. Can you see my screen? There's always evil everywhere. There's always evil everywhere. Hira Tabir, how are you? Awesome. Hi. Okay, so let me get back to this. Right? We were on this fellow? Okay. Anyways, so let's start. Back to where we left off at. Alrighty then. All right. Okay. Yes, Ramesh, I got disconnected. I had a power outage. There's something not in my control. Thank you for reminding me that, yeah. And I'm on my generator now, but it took time. The whole thing shut off. All right. So these are energies that are measurable. These are energies that are not measurable, and hence we call them potential energy. Meaning they give something the ability or the potential to do work. They are there. They're inertly there, but it's an ability to do work. It's not always present. It's not always measurable. So the most common potential energy that you look off in physics is gravitational potential energy. That's the one you see in physics. I'm talking about this fellow. This is potential energy that are possessed by certain chemicals, and because they have high energies, we call them fuels. These are fuels that have high energy that end up giving out energy, and so that comes in handy for us later on. Okay, bhai, how do we use them? We use them obviously as fuels to provide us with energy that we need for many and many other things. Yeah. So now, where does this energy come from? And that's somebody's good question. And the energy comes from other changes. Now, for chemicals like a fuel, so if I'm telling you that CH4 was a fuel, so when carbon and initial hydrogen elements, when they must have made methane, they must have taken in the energy from the surroundings, and already existing heat energy from the surroundings was converted to chemical potential energy over time. That's why, not everybody has it. It's something that we can mine for. We can dig up in oil deposits under the ground, and we get energy, we get fuel from there, because these fuels were made over centuries, slowly carbon and hydrogen combining, absorbing energy from the surroundings in small bits, and they had converted that heat energy and became a store. You can think of them like batteries, that they become batteries for chemical potential energy that they had stored much earlier. And now human beings end up burning this energy to produce products, but they also give off energy. And this is the concept that I need people to understand, because I get kids in A levels that cannot understand the concept of chemical changes in chemistry. It's a very simple energy transfer process. Energy is converted from one form to the other form. Sometimes it's converted from chemical potential energy to heat energy, and sometimes it converts heat energy to chemical potential energy. There's always conversion happening. So if even somebody has energy right now as a fuel, they have gotten it as a chemical from reactions in earlier times. And at the basis of all of this, if you go back in time and trace all the chemical reactions, they're all based on the big mother of all reactions, called the Big Bang. Yeah? So the Big Bang was the first exothermic process. For those of you who is using the term, we'll talk about exothermic and endothermic in a bit. But the Big Bang produces energy. That energy is absorbed by chemicals to become other chemicals over time, and those are the chemicals you use as fuels now. And the Big Bang did create energy. So this law of conservation of energy is only true for a certain scenario. The Big Bang mein energy was created. Yes, there was. And then we go on to nuclear physics and other areas that we do create energy from mass. But in most cases, if mass stays constant, then energy is not created or destroyed. Now, yes, Mesa, we'll get back to that in a bit. So far, are we on the same page? All everybody? Everybody? Yeah. Yeah? Alright. Then, moving along. What do we have? Any questions about now potential energy and everything else before I continue? All good? Okay. Done. So the next thing, what are we doing on the next thing? So how do we measure? So first of all, our job will be there are two things. Can we calculate these energy changes and how we can measure these energy changes? So what you have is, you have reactants making products. So let's say we have reactants making products, and this has an energy change accompanying it. So there's an energy change. Now we need to be able to measure it, and can even calculate it or predict it. So both things you're gonna see. Okay. How do we measure energy changes? We measure them by using a thermometer. And many reactions can be found out through thermometer. Like you literally have, like I'll give you a good example. We've done this before. We've done this, that acid can react with an alkali. Both are liquid aqueous to produce salt and water. And we know that this reaction gives off heat energy. A very easy way to find this reaction's heat energy is to literally take the reaction in a container and measure the energy change. Yeah, that's what we can do. Yeah, there is a difference between measuring and calculating. Measuring is using a thermometer in the lab scenario where you measure temperature rise or delta T, as in you measure change in temperature. And once you've measured the change in temperature, then you calculate it. The calculation is to do with something known as bond energies. Then that we can use using, we'll talk about that later, using bond energies is what we do. All right. So there is a difference between bond energies and thermometer measuring calculation. So in the labs we can use thermometer to measure enthalpy changes. Now, and one good example is if you take a beaker and you take an alkali and you add an acid to it, you're gonna get heat given off. That's a given. And you can measure the temperature rise by literally inserting a thermometer in the system, and you get a temperature rise, and using that and certain physics that you don't have to worry about, but for those of you who've taken physics might recognize this, that you can measure the heat by using formulas of MC delta T, the mass of something, its specific heat capacity, and the temperature change. But this you won't be worried about in O-level chemistry. You don't have to worry about this. Yes, you should be able to measure it with a thermometer and read a thermometer, but you won't be doing this calculation. Not at all. You can ignore this calculation. Now, there are two types of chemical reactions. Very simply speaking, you have a reactants becoming products. What's the formula of heat in simpler words? That's an oxymoron, Dilavar. You can have a formula in simple words. The formula is, in a way, the simplest words. It can be made more simpler or at least shorter. You know? Yes. Ignore that formula. We don't use it. Alright? So I'm saying there are two types of reactions. When they go from reactants to products, either they can produce heat, or they go hot, or they go cold. Okay? Either they produce heat. So when they go hot, it's actually chemical. So that type of reaction is chemical potential energy becoming heat energy. And when they go cold, they actually convert heat energy to chemical potential energy. And those are two different reactions in chemistry. Like the one above, this one for us is any reaction that produces heat. In fact, what it means is it is hot, is an exothermic reaction, meaning heat is being produced for the system. And the other one is called an endothermic reaction. So an exothermic reaction more correctly can be known as something that takes in chemical potential energy and produces heat energy. And one reaction that goes cold converts heat energy to chemical potential energy. Now, understand that for this reaction, the internal energy is decreasing, which is another name for potential energy is internal energy. You can't measure it, but it's there. So when internal energy decreases and it becomes heat energy, that's called an exothermic reaction. So first of all, you should learn this, that if a reaction goes hot, produces heat, like a stove burning, that's exothermic. If it goes cold, it's endothermic. Your freezer causes an endothermic change, actually. Another is those cold packs, those packs that you can break off and suddenly they feel cold in your hand. Those are endothermic reactions. There aren't too many endothermic reactions, but there are enough for us to study. Alright? So, let me say this again. There are two types of chemical changes, endo and exo. There are two types. Alright? Any questions? Evaporation is endothermic. Yeah? Chemical potential energy. I never use the word chemical energy, boss. I use the word chemical potential energy. Difference. Yeah. All right. Yeah. All right. So now let's say we could measure. Now what happens is that, look at this, is a good way to see it. Something like this, you know. Let's say this is my starting mark. Okay. In fact, no, not duplicate. If I'll copy this, and move it down for later. So basically, let me show you something. There are two types of reaction. Let's say you start off from something. Let's say you start off from a certain level. Now, what is the y-axis here? Now, this can be considered as a energy scale. Now, which energy? Not thermal energy, but this could be considered the internal energy of chemicals, also known as the chemical potential energy. So, internal energy or chemical potential energy. So, internal, your books will say energy, hence I am writing energy, but it's chemical potential energy. Then reactants. Now sometimes the reactants have more internal energy than products, and so for example the products might have lower internal energy or lower chemical potential energy. So that change right here, this change is basically you could think of this is decrease in internal energy, and the only way internal energy can decrease is when the internal energy or chemical potential energy is converted to heat energy. So you could say that chemical potential energy is being converted to heat here, and we call this an exothermic reaction, where the product I have has less energy than the reactant. This is the scale. So reactants have energy, products have less energy, and the decrease in energy is given off as heat. So this decrease is given off as heat. But sometimes, and in there's some reactions where the products have more energy than reactants, and the only way that can happen is if the heat from the surrounding area or a human being explicitly providing the energy, that heat from any other source can be taken and converted to chemical potential energy. Here CPE stands for chemical potential energy, also known as internal energy. This is CPE. They don't write it chemical potential energy, they just write it energy, which I find so stupid, because which energy are they talking about? They are talking about the internal energy of the reactants and products, which is also known as chemical potential energy. So either the reactants have more energy and the products have less, and that change means that energy has to be transferred to some other form. So when they go from reactants to make something, and a good example is your methane gas, that burning goes to products and gives off heat, and therefore we call it an exothermic reaction. The other one, the opposite, is an endothermic reaction, and in that case the products making have more energy than the reactant. Alright, and some of them, now in your biology, you know, there are two very important reactions. One is photosynthesis. Photosynthesis is a very good endothermic reaction example, because what it does is it takes light energy and converts it to chemical potential energy in the plants. This is how plants make their food. The food is the fuel. How do they make the food? They take the light energy from the sun and convert it to chemical potential energy. On the other hand, respiration. Now anybody who knows any simple biology knows that respiration is your burning of food in your body. It's when you convert food in your body to energy. And that is an exothermic process, because the food has higher chemical potential energy and it forms a product which has lower chemical potential energy, and the energy released is given off as heat that your body uses as energy in other forms. So you're moving your muscles and everything else and so on and so forth produces that. Yeah. So exothermic, endothermic. A very good way of learning this is respiration and photosynthesis. When plants make food using light, they are converting light or heat energy from the sun to chemical potential energy. When the food is being eaten by humans, it's taking the same food of the plants and converting that into energy for themselves. And so they had more energy as food, but the energy is given off. To make food from carbon dioxide, that's what happens. If you want to be more technical, it's glucose becoming carbon dioxide, glucose becoming carbon dioxide, and in photosynthesis, carbon dioxide becomes glucose. All right. So respiration is an example of exothermic reactions. Photosynthesis is an example of endothermic reactions. And you have to know this. In exothermic, the products have less energy than the reactants. Very simply speaking, if I tell you that this is a reaction of glucose, C6H12O6, and 6 oxygens makes 6 CO2 and 6 waters, that 6 CO2 and 6 waters has less energy than the glucose. And vice versa, in endothermic reactions, the products have more energy than reactants. So it's how we look at it. Reactants becoming products is exo if energy is given out. And if energy is increasing or going from reactant to product, products have high energy, the heat energy is being converted to chemical potential energy, the things will feel cold. Literally, if you're holding a if you're holding an endothermic reaction in your hand, it's going to feel cold. If you're holding an exothermic reaction in your hand will feel hot. That's how hot and cold the difference is. You need to internalize this for yourself. This has to make everyday sense. If you touch a chemical reaction and it feels hot, it is an exothermic, external heat. If you touch a chemical reaction and your hand feels cold, then you're feeling an endothermic reaction. Always remember that. Thank you, Arisha. I'm so glad you find that fun. The rest of you, was this a good enough explanation so far? Hi, Ramesh. Or did Ramesh run away? I think Ramesh didn't like your comment. Dilaver. I think he didn't. Homie chill. I think he got offended. Oh well. It's okay. Life's too short to be offended by things like this, right? Anyways, all right. Awesome, guys. So, yeah. All right. Yup. So I'm gonna end this here right now. All right. I'll see you guys again tomorrow. Is ice making endothermic? Actually, if you ask me, Ice is exothermic because the energy of the water is being sucked out by the, because making ice is not a chemical change, you see. That's why it's counterintuitive to what you just heard. All right, Mesa. But so making ice from water is actually exothermic. The water is losing heat that it has to the refrigerator, and so it has less energy now and it become ice. Remember, ice has less energy than water and steam has more energy than ice. So simply speaking, does ice have less energy than water, or does ice have more energy than water? We all know ice has less energy than water. The molecules are vibrating less, so less energy. So it's giving heat to surroundings. Yes, it is giving heat to surroundings. That's why it's exothermic. Yeah. Making ice is exothermic. All right. All right. Ciao, guys. I'll see you guys next class. Yeah. Thank you. This was awesome. I'll see you again. Bye. Bye. See ya.